Hello all of you. So, in the last lecture we have discussed how a binomial distribution approaches a Gaussian distribution. We first did the coin toss example and basically re-established the center limit theorem, and then towards the end of it I introduced the problem of a Drunkard walk. So, today we will complete the Drunkard walk example, and then I will also introduce the idea of Lagrange multipliers, that is, as I said, is a more systematic way of including constraints in the minimization or maximization. So, just to quickly recap the Drunkard walk problem. So, a drunkard starts from bar and he is fully unconscious. So, he is totally forgotten where his home is. So, he is making steps to the right or to the left randomly, but with equal probability to the right and left. So, let us say he moves to the right in the first step, then he can come back to the left, again to the right, again to the right, can come back, and there are a large number of possible ways in which this can happen. And then I said, let us say if he makes n steps in total, and out of this n plus are to the right and n minus are to the left, then the net displacement after n steps is n plus minus n minus, and therefore, if his home is say d steps to the right, he can get there in n steps for this particular value of n plus and n minus, right. And so, the idea is that even though the average displacement may appear to be 0, because the going to the right and left are having the same probability, he is undergoing a displacement in certain number of steps, and therefore, he is likely to get to his home. So, now we are interested in getting the most probable distribution for this case, and then to find what is the probability that he can get to his home. More specifically, we want to find the width of the distribution in this case, that will characterize how much he is able to move from its position on the bar. So, W was equal to n factorial by n plus factorial n minus factorial, and we already have found n plus is n plus t by 2 and n minus is n minus t by 2, and therefore, W is n factorial by n plus d by 2 factorial n minus d by 2 factorial, and the objective for us is to maximize ln of W by using the Stirling approximation that we already have stated, because capital N is very large. So, essentially what we have is ln of W can be approximated as n ln n minus n minus n plus d by 2 ln n plus d by 2 minus n plus d by 2 minus n minus d by 2 ln n minus d by 2 minus n minus d by 2. You may notice that if I add n plus d by 2 and n minus d by 2, we get n that cancels with the n that we had here. By the way, this would be a plus sign here. So, therefore, when I want to minimize this, we are ultimately interested in d. We want to maximize this. In this case, the extremum relation is dou ln W by dou d equal to 0, and the first term will be 0 because n is a constant. The second and third term will appear. So, this gives me and then we have a minus half here because we take a derivative of n minus d by 2 with respect to d, and then we have again a minus half appearing here, and that is equal to 0. Again there are certain cancellations. So, what we see first is that we have a plus minus half here and a plus half here, these two cancel out, and then half cancels out because that is being equated to 0. So, what I essentially have is ln of n plus d by 2 is equal to ln of n minus d by 2. That means for the most probable distribution, let me call it d star, we have this, and therefore d star should be equal to 0, which should not come as a big news because the probability of going to the right is same as probability of going to the left. So, the most probable displacement is equal to 0. But just like what we did for the coin toss example, we are actually interested in the distribution of ln w around this particular point d star or this particular displacement d star. So, for doing that, I again use the idea of Taylor series. So, I want to expand the function f x around x 0, and the way to do that is this. In this case again f is same as my ln of w, and x naught is same as my d star, and x is some value d for the displacement. So, then again we have f prime of x 0, that is equivalent to dou ln w by dou d, that is evaluated at d star, and we already have found it earlier, that is right here. So, you have minus 1 by 2 ln n plus d by 2 plus 1 by 2 ln n minus d by 2. That is what we have found in the previous example, and this is equal to 0, clearly because that is the condition we used for the extremum anyway, right. So, what is of more interest is to find the second derivative. So, second derivative is going to be dou 2 ln w by dou d square at d star, which is dou by dou d of dou ln w by dou d found at d star, which gives me dou by dou d of whatever we had here and that is at d star, and this comes out to be Again we have certain cancellations, and essentially since I am evaluating around d star and d star equal to 0, you can see what do we get from here. What we get is something like minus 1 by n from there. So, now if I put this back in the expression that is right here, what we see is f of x is equal to f of x 0 plus this first term goes to 0. So, what we have is second term x minus x naught square by 2 factorial, or in terms of ln w of d is ln w of d star, and what we have found is that f double prime is minus 1 by n. So, we get minus 1 by 2 multiplied with 1 by n. So, we have minus 1 by 2 n d minus d star whole square. So, this we can write as w d as w d star exponential of minus 1 by 2 n d minus d star whole square. And if I again compare with the expression of the Gaussian distribution, it is important to mention here that whenever we compare this, I am only comparing the term inside the exponential, not the prefactor, right. And the reason for this is the following. So, if you recall, if I am looking at a probability distribution function, if I integrate that over the entire range, that must be equal to 1, right. So, the prefactor essentially is a normalization factor that will apply there, and that factor should be such that the probability integrates to 1, right. So, of course, the prefactor need not be the same between the binomial distribution and the Gaussian distribution, or whenever I go from a discrete to a continuous distribution, the prefactor may change, but the term inside the exponential is the one, that is what we have to compare. The prefactor has to come from the condition that the probability is normalized or it integrates to 1. So, now if I compare this, then d is analogous to x and d star is analogous to x bar, and so we have 2 sigma square going like 2 n, and therefore, sigma square goes like n. We basically get the same result as we had for the coin toss example, that is my standard deviation goes like square root of n, that is the number of steps I am making. In the earlier case, it was number of tosses, now it is the number of steps, right. Because this is also a binomial distribution, just like what we had for the coin toss example. If I now look at my WD versus D, this is going to be a Gaussian distribution, and the width of that corresponds to sigma, and sigma is going like square root of n, right. Now, we already have said that sigma is also the square root of variance, or sigma square is the variance, right. And what is variance? Variance is the characterization of the deviation from the mean, right. So, we can also write sigma square as the average deviation from the mean value. That is, since d star is equal to 0, we have d square going like sigma square. So, therefore, d square in this case goes like n, because sigma square is going like n. We have to be slightly careful here, because the plus displacement and the minus displacement, the plus d and minus d, give the same value of d square, and therefore, there will be a factor of 2 that will come in here, but that is beside the point. The main point is that my mean square displacement is going like the number of steps that I am making. So, even though the average displacement of the drunkard walker or a random walker in one dimension is 0, the mean square displacement is quite significant, and in fact, it is linear in the number of steps that the random walker is making. And this has a very strong analogy with the diffusion process or the molecular movements inside a thermodynamic system or a room. So, let us say, for example, if I look at molecules present in a room, the molecules are undergoing collisions with other molecules. Every time they undergo a collision, their direction of motion changes, because now the other particle may be coming at a different velocity at a different direction than the particle in question. So, once they collide, then the original direction of the particle will change and the original velocity will change. So, what may appear like is that any particle is undergoing many collisions as it is going along, and that is similar to a random walk if I focus on a particular particle in the system. So, let us say, for example, you have a system of molecules, and I define the motion of a particular molecule here. Now, as it starts moving with the velocity that it is moving, this will undergo collisions from the other molecules. As soon as they collide, the direction and the velocity of the molecule changes, and this keeps happening throughout time that it is moving inside that system, because the collisions are so frequent, and since the particles may come from any particular direction, the collisions can be in any particular direction. So, for us it may appear like it is undergoing a random walk, right, and this essentially is the idea of a diffusion process. Whenever we talk about a diffusion process, it essentially refers to motion of molecules as a result of the collisions they experience from every other molecule. And what is special about diffusion process is that at any given time t, the mean square displacement, or typically it is called r square, it does not go like t square, but it goes like t. And why should it go like t square? Because let us say, for example, the same guy was moving and it does not undergo any collision, then it will move with certain velocity v. So, at any given time, the mean square displacement from the original position will go like v t square, and provided the velocity is constant, this should go like t square. That is the whole idea of rectilinear motion when it is moving at a constant velocity. When it is undergoing collisions, its direction and velocity keeps on changing, and which gives me the diffusion regime where the mean square displacement goes like number of time steps or the time, just like for the random walker case it was going like the number of steps. We can divide the time into small intervals and say that it is one step of the motion of the molecules, or we can say that this is the time the molecule takes to travel its mean free path, and if I do that kind of a connection, I can make connection between the number of steps of random walker and the time taken in a diffusion process. And the key idea is that in both these cases, the relation between the square displacement and the time or the number of steps is linear, and it is not proportional to t square as you expect in the case of a rectilinear motion. We will come back to this example, although we have done for a one dimensional case. The same result one can get also for a walk in 2 dimension or 3 dimension. Actually, this can be generalized to pretty much a continuous space, just like what molecules have. They can move in any particular direction, not really in along x or along y. They can move in any particular direction in 3 dimensions. But the basic result that we have obtained, that the square displacement proportional to n is generally valid irrespective of what dimension that we are solving the problem in. So, with this particular idea, I now move to the description of Lagrange multipliers. We already have introduced why it is an important concept. It helps when we are interested in minimizations with respect to certain constraints. So, let us say for example, I want to maximize or for example minimize, since we already did first derivatives, whether it is a maxima or a minima can only be established by looking at second derivative. So, we are actually doing an extremization problem. A function that is a function of variables x1, x2 to some xr. So, I want to find the values x1, x2, xr that maximizes this function, but this is subject to certain constraints, and that is some function g of these variables that is equal to 0. So, in this particular case, the maximization problem can be stated like the following. So, what we do is we do dou f by dou xj, where j will go from 1 to r, minus something called the Lagrange multiplier, typically denoted by lambda, multiplied with dou g by dou xj is equal to 0, and this is for all values of j. So, for all values of j, the lambda variable remains the same. Of course, the derivatives are going to change. If you have more than one constraint, let us say we have, instead of one, let us say we have 2 constraints g1 and g2, which can be any function. The functional form is not very important here. Then we have 2 Lagrange multipliers, in fact, for every constraint I will basically add 1 Lagrange multiplier in the picture, and the number of Lagrange multipliers are equal to the number of constraints that we have in the problem. So, let us see how it works in practice. So, let us say I go back to that example that we have been doing of binomial distribution. So, we have n tosses which can result in n1 heads or n2 tails, or I am distributing n entities into 2 baskets, n1 and n2, or it is a random walker making n steps. Whatever is happening, the key point is that it is a binomial distribution, and we had a constraint n1 plus n2 is equal to n. So, I can also write this w as in fact n1 plus n2 factorial by n1 factorial n2 factorial. The reason why I am doing this is that now I am separating the equation from the constraint. When we did the example earlier, I replaced n2 with n minus n1. So, I eliminated one variable because of the constraint. Now, we no longer eliminate that variable because we separately account for the constraint. This approach becomes more useful when we have more than one variable or we have a multinomial distribution, but the idea is generally valid, right. So, then the way we handle this is that this becomes my function f. Actually, we are interested in ln of that. So, f can be ln of this, and I want to maximize f with respect to n1 and n2, where n1 and n2 must satisfy this constraint. Now, if you recall, the constraint was written in the form that the right hand side was equal to 0, which we can do in this case as well. So, I can write my g as n1 plus n2 minus n is equal to 0. So, if I state the problem in this way, I re-emphasize, I am no longer using the constraint to eliminate any variable in the problem, and every time we had capital N, we can replace with n1 plus n2, because the fact that n1 plus n2 is equal to capital N is taken care of in the constraint equation. That really makes it much more systematic than what we have been doing earlier. So, now the maximization problem reads dou f by dou nj minus lambda dou g by dou nj is equal to 0. In this case, j is equal to 1 and 2. So, let us say if I want to do for j equal to 1, then we have dou f by dou n1 minus lambda dou g by dou n1 is equal to 0, and this becomes, we can already use the Stirling approximation, and this will be n1 plus n2 ln of n1 plus n2 minus n1 ln n1 minus n2 ln n2. Keep in mind that there was one more term there that got cancelled, and then this will be, you can do this and you will find that it will be equal to 1 plus ln n1 plus n2 minus 1 minus ln n1, that is my dou f by dou n1, and dou g by dou n1 is simply derivative of this, that is simply 1. So, this is equal to 0. So, what we have is ln n1 plus n2 minus ln n1 is equal to lambda. And now, if I do the same thing for n2, what we get? Ln of n1 plus n2 minus ln of n2 is equal to lambda. If I compare these two equations, or you can subtract it, what you notice is that ln n1 must be equal to ln n2. If I simply subtract this, then this will, these two will cancel, these two will cancel, and we will have ln n1 is equal to ln n2, that is n1 is equal to n2, and we already had this particular constraint. So, if n1 is equal to n2, we can clearly see that n1 is equal to n2 is equal to capital N by 2, because only then it will satisfy this particular constraint. So, it is the same minimization problem that we have done earlier, with a small twist that we no longer eliminate any variable when we write the function, we take care of the constraints separately by including a Lagrange multiplier. And you will see later that how it becomes extremely useful when we apply it to the in the context of the thermodynamic functions that we will do later. So, with that I conclude the discussion for today's lecture. Thank you.